Welcome to FEM Global Academy, and I'm your favorite physics teacher, Fred Mack. We're talking about dimension of physical quantities. Now, what are dimensions? Dimension simply means a way physical quantities can be related or connected to fundamental quantities. Remember, in our last two topics, we talked about what fundamental quantities are. So dimension is a way we can use physical quantities to relate or connect fundamental quantities. And this method of dimension can be used to find the relationship between quantities, and when mathematics become too difficult. So they are used to, the method of dimension is used to find a relationship of quantities when mathematics becomes difficult. Now, once again, I want to tell you that dimension is quite different from units. Dimension is quite different from SI units. Now, take for instance, I said before that the three most important basic quantities are mass, length, and time. Now, mass. Mass has an SI unit as kilogram. But the dimension of mass is M. The dimension of mass is M. Now, length. Length is in meters in SI units, and the dimension of length is L. The dimension of length is L. Now, distance could also represent length. So I could say dimension of distance is also L. Distance. The dimension is also L. Now, if I want to talk about the distance between point A to point B, between point A to point B, somebody will say is the length from A to B. Another person will say is the distance from A to B. And so length and distance, they are practically the same when it comes to dimension. So I use L to represent both distance and length. Now, time. The SI unit for time is seconds. Please, let's take note of that. Seconds. But the dimension of time is T. Capital letter T. The dimension of time is T. Now, electric current. Electric current. Electric current, the symbol is capital I. The symbol is capital I. And then the SI unit is ampere. And the dimension is also ampere. A. And the dimension of electric current is capital A, which is ampere. Now, I want to let us know that things that are very, very paramount in physics. Number one is the formula. Number two, the SI units. Number three, the definition. Once you're able to know a formula of any parameter, to coin out the definition becomes very easy for us as students. So you know, number one, that the symbol is very important. The SI is very, very important, because 2 could mean anything. I said number 2. 2 could be in centimeters, 2 could be in kilometers, 2 could be in ampere, it could be in volt. I don't just say 2. So the SI unit of what I'm talking about should be made mention. So SI unit is very important. Symbol is very important. The formula, very important. The definition, very important. So if you can know these things, physics becomes very easy. Very easy. The SI unit, the symbol, the definition, and the formula. From the formula, you can be able to coin out the definition. You may not speak much grammar, but from the formula, you can be able to coin out the definition. But the SI unit is very, very important. So let's continue. I'm talking about universe Luminous intensity. Luminous intensity. The dimension is double line. This is the dimension for luminous intensity, double line. Then temperature. Remember, all these I'm naming now are under fundamental quantities. So dimension is a way that we can use physical quantities to relate or connect to fundamental quantities. The temperature, the dimension of temperature is K. K is now the dimension for temperature. Luminous intensity, double lines, two equal lines is the dimension for luminous intensity. Electric current, A, which is representing ampere, is the dimension for electric current. Time, which is measured in seconds, the dimension is capital T. When you say small t, it means a different thing entirely. Then distance is representing as L. Also, this distance is representing as L as a dimension because distance and length are the same when it comes to dimension. Then mass is measured in kilogram, but the dimension is capital N. Capital N. Now let's now put these things into practice and see how it goes. Okay. Having known that the dimension for mass is M, the dimension for length is L, the dimension for time is capital T. Now let's put it into practice and see how it works. So follow me closely. Let's take for instance speed. I said that formula is very important in physics. For those who are beginners, learn every definition and every formula you come across when it comes to physics. For those of us who are already preparing for our jams or preparing for our YF, we are conversant with these formulas. So it's just how to apply them. That's where the problem comes in. Now speed, for instance, speed is a parameter. Now what is the formula for speed? Speed is distance over time. Distance over time. Distance over time. Distance traveled in a given time. Distance over time. And the SI unit is meter per second. Meter per second. Meter per second. Distance is in meters. Time is in seconds. So the power there means division. This and this is the same. So if I'm writing this and writing this is the same. But preferably write it like this. Distance over time. Distance is measured in meters. Time is in seconds. So the SI unit is now meter per seconds. Speed is the distance traveled in a given time. Distance traveled in a given time. And the dimension now, because we're talking about dimension. Dimension for distance, remember I said is what? L, and T is what? T. Now this is not a dimension for speed. So this is also the same thing as what? These are LT minus 1. LT minus 1. So we write like physics students. So we preferably use this LT minus 1. LT minus 1. This is the same thing means meter per second. So from here too, I can able to find out this. Meters is in length, time. Seconds is time. So LT minus 1. LT minus 1 is the dimension for speed. Is the dimension for speed. Now, velocity. Let's say about 2. Let's say velocity. Velocity is displacement over time. Displacement over time. Displacement. Over time. Displacement, speed, somebody could say speed and velocity are alike. but they are not the same. One is a vector quantity and the other is a scalar quantity. Now, speed is a scalar quantity. Talking about distance with time. Now, good. Now, number two, let's talk about velocity. Velocity is distance traveled in a specified direction. Distance traveled in a specified direction. So, this velocity is displacement over time. When it comes to formula, displacement over time is distance traveled in a specified direction. Now, somebody would say that speed and velocity, they are the same. They are not exactly the same. They are not. Now, speed is a vector. Speed is a scalar quantity. Speed is a scalar quantity, while velocity is a vector quantity. Now, this one is talking about distance. This duration is not specified. There is no direct specification. Take, for instance, move from just take 10 steps. Take 10 steps towards me. The teacher said, take 10 steps towards me. You don't know where is it, to the 10 steps to the east, or 10 steps to the west, or to the south? Is it backward? Is it forward? Is it by the side? You're not aware. So that is speed. Move 10 centimeter or move 10 kilometer or move. You're just moving. There is no specific direction. But if you are asked to move 10 centimeter due east, it means it is not specified. That becomes velocity, no longer speed. So speed is distance traveled in a given time, no specified direction. While velocity is the distance traveled in a specified direction with time. And the formula is displacement over time. And they have the same SI unit as in meter per second. Displacement is equally distance. So it is meter per second. So the L dimension still becomes L over T, which is LT minus 1. LT minus 1. The similarity between speed and velocity is, one, they have the same SI unit and they also have the same dimension. But the formula is quite different and the definition is quite different. One is a vector quantity and the other is a scalar quantity. But they have the same SI unit, yes. They have the same dimension, yes. But they are still not the same when it comes to definition. Number three, let's go to, let's say, area. Area. Now, area in terms of formula is length times breadth. Length times breadth, or length times length. Length times length. If it is a square, it becomes length times length because all the sides are equal. If it is a rectangle, it becomes length times breadth because all the sides are not the same. So length times breadth is the formula for area, and the SI unit is meter square. So the dimension, remember we said the dimension for M is in meters, but that is the SI unit. Remember we said that length is represented as what? L. Another length is also L. So the dimension for area is L squared. L squared becomes the dimension for area. Length times length becomes L squared. And the SI unit is meter squared. Please do not mix it up. Dimension and SI unit are not the same. But the SI unit will help you in finding the dimension. Number 4, let's continue. Number 4, let's say volume. Volume is also length times breadth times height. Length times breadth times height, or length times length. And because when we talk about breadth, it's still length. Because about height, the height of an object. My height from the ground to my head is also my length. Is my height, is my length. So length and height, they are the same when it comes to dimension. Literally in definition, they are the same. This height of this person, the length of this person is the same. If I measure my length and I'm measuring my height, they are saying the same thing. So volume is length and length and length. And the dimension becomes L3. The SI unit is meter cube. Meter cube is the SI unit for volume. And then L cube is the dimension for volume. L cube is the dimension for volume. So let's continue. I think I erased so that I have enough space to write. And I hope you are gaining something. If you are gaining something, so just pay attention. Because I bet you are just joining us now. We are still talking about dimension of physical quantities. Dimension of physical quantities. How we can use physical quantities, connecting them to fundamental quantities. Now let's say force. Force. Force has a formula as mass times acceleration. Mass times acceleration. Before then, let's talk about acceleration so that it becomes clearer for you. So let's pause there. Acceleration. Acceleration is rate of change of velocity with time. Change in velocity with time. With time. Now this is acceleration. Change in velocity with time. Change in velocity with time. And remember, from our dimension of velocity, velocity is length LT minus 1 as our dimension. LT minus 1 from displacement over time. We are having LT minus 1 all over T, because the dimension for time is T. So we are having T. So if this T now goes upward, because this one still becomes this, can also be LT minus 1, then minus 1. Because if this is going up, the opposite side, 1 is there. But if it goes up, it becomes minus 1. T there has 1 already. And you don't put it there. Now, we are talking about force is equals to mass times acceleration. I said, let's now go to acceleration first, before I now know the dimension for acceleration to add it into the formula for force. I'm having acceleration as velocity over time. That is rate of change of velocity with time. That's acceleration. Rate of change of velocity with time. And remember, we did velocity. Velocity is LT minus 1. That is a dimension for velocity. Velocity is displacement over time. Please do not confuse it. Velocity is displacement over time. And the dimension is LT minus 1. LT minus 1. So LT minus 1 as the dimension of velocity. T is T. Time is T. Time is T. And mathematically, if I put 1 here, you just know that T is raised to power 1. It's just there. But if I put it now, it doesn't look well. So then you just know that once you are seeing a letter there and it's just on its own, it's representing 1. So T is 1. And if I take it upward, because this thing becomes is equivalent to LT minus 1 over T. So this and this is the same. So if I take it upward, they will be in the same line, becomes T goes up as 1. So it becomes minus 1. Since it's a positive sign 1, it's going up, it changes to minus 1. So it becomes LT minus 2. And this is now the dimension for acceleration. LT minus 2. LT minus 2 is the dimension for acceleration. And the SI unit is meter per second square. Meter per second square. That is the SI unit for acceleration. But the dimension is LT minus 2. Lt minus 2 is the dimension for acceleration. Now, let's go back to force. I said force is mass times acceleration. So it becomes easy. What is the dimension for mass? M. Now, what is the dimension for acceleration? Lt minus 2. Lt minus 2. So, how you can use it to solve mathematical problem? When you are forgetting what acceleration is, you can now go back to the definition, velocity with time, and then find the dimension, and then put it there. If you already know it, you just impute it, Lt minus 2 as the dimension for acceleration. Put it together. This becomes mLt minus 2. This is now the dimension for force. mLt minus 2, T minus 2 becomes the dimension for force. Becomes the dimension for force. Let's continue. Let's look for another. Let's say density. 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 Density is mass over volume. Mass over volume. Mass over volume. Yes, people will say I have a lot of formulas when it comes to physics. Yes, you have a lot of formulas to do try as much as you can to learn this formula, let them become part and parcel of you. When you know these formulas, physics questions become easy to solve. You know the formula everything, just to apply it becomes easy. So you do as much as you can to learn as many formulas as possible, which you're going to be learning in this course. As many as you have gone through, put them at the back of your mind. Don't let it go. You not add to what you have known before. Don't throw it away. Now, density is mass over volume. Now, the SI unit is kilogram because mass is kilogram. Volume is meter cube. Kilogram, meter cube. Kilogram, meter cube. So if I put it together, it becomes, in terms of SI units now, it becomes kilogram per meter cube. Kilogram per meter cube. The per means the division. If you leave it like this, you are still correct. But this is better because we are evolving, we are growing. This is better. Kilogram per meter cube. Now, this is the SI unit for density. But dimension now, dimension is for M is what? M. Dimension for mass is M. Over volume is length cube. We've done that before. We said volume is length and length and length. So volume is length cube. So if I put together the same way, it becomes ml minus 3. So then when I ask, where is the minus coming from? Yes. Once this thing goes up, because of the division, it changes to what? Minus. Because as I assume there is positive sign, this is plus 3. You don't just put plus 3. So when I see it, I know it is plus 3. So once it goes up, it becomes minus 3. So this is now the dimension for density, ml3, ml minus 3. And let's continue. Let's say energy. 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 So we have enough space. Okay. Good. Energy. Energy. Energy is mass times gravity times height. Mass times gravity times height. It could also be half mv squared. And when we get to that stage, we're talking about the different types of energy, potential and kinetic energy. But for now, energy, mass times gravity times height. So mgh, mgh, mgh. Now mgh, this M, this is also gravity is also about acceleration due to gravity. Acceleration due to gravity. And still, when it comes to dimension, it is still A. Gravity is the same thing as what? A. And then height is also L. Distance. Now, this one still remains as M. Sorry, this now LT minus 2. Remember, the acceleration is LT minus 2. We have done that. LT minus 2 times L. LT minus 2 times L. So this now becomes N times length, L square T minus 2. NLT minus 2. Now this is now the dimension for energy. NL square T minus 2. This now becomes the dimension for energy. And energy, it can also be in the SI unit is now joules. Joules is the SI unit for energy. Energy is measured in joules. Energy is measured in joules. Okay? It can also be, if you can count it from here, remember mass is in kilogram, gravity is in meter per second square, height is also in meters. So it becomes kilogram meter square per second square. So if I'm using this or this, we are saying the same thing. We are saying the same thing. So the SI unit for energy could be kilogram meter square per second square or joules. But joules is popularly known as the SI unit for energy. But if you write this as a student, you are equally correct. But like I said before, we evolve, we are growing. The standard unit for energy is in joule. So when it comes to those who are performing the right way, joules is absolutely preferable to as the SI unit for energy. But if you are writing kilogram meter square per second square, you are equally correct. Nobody's going to mark you down. You are equally correct. It's the same. Now the dimension now for energy is ml square T minus 2. This now becomes the dimension for energy. Another one, let's still continue. Let's talk about power. Power. Now, power is work done over time. Work done over time. So before that, since it's work done over time, let's now know what is work done. So let's go first. You come back to this place. Work done. Work done is force times distance. Now this is the formula for work done. Remember I said in physics, formula is very important, SI unit is very important, symbol is very important. Formula, symbol, SI unit, definition, very important. But please take note of the formula and the SI unit, very, very important. So work done is the formula for, work done, force and resistance is the formula for work done. Remember we have done force before. Force is MA in terms of formula. MA times what? Distance. So M is also the dimension for mass. Then acceleration is LT minus 2. That is the dimension for. So we have done it before when we said acceleration is change in velocity over time. And after our calculation, we got that LT minus 2 is the dimension for acceleration times L. So remember that L is also the dimension for distance. So if I put it together, it becomes ML square T minus 2. And energy is the same when it comes to dimension. Work done and energy, look at it very well, they have the same dimension. And work done is also measured in joules. Work done is also the SI unit for work is joules. the SI unit for energy is equally joules. They have the same SI unit, they have the same dimension. And let's now go on now to work, to power. Power is work done over time. Power is work done over time. So if I know what work done is as ml squared t minus 2, so work done becomes ml squared t minus 2 all over t, because time is what? T. ml squared t minus 2 all over t. Remember I said here it has 1 as the power there. T raised to power 1 is there, but you don't write it. You don't write it, but you know that there's 1 here. There's 1 here. So as I'm looking it upward, it becomes what? The T becomes what? Plus 1. Sorry, minus 1 is plus 1. So when it goes up, it becomes what? Plus 1. Now it's plus. If it's going up, minus 1. If it's minus 9, when it's going upward, it becomes plus. Once a sign is moving upward, the sign will change. If it's a positive sign, it will change to negative. If it's a negative sign, it will change to positive. So if I combine this one together, it becomes ml squared t minus 3. Or minus 2 minus 1 is minus 3. So this now becomes a dimension for power. ml squared t minus 3. The t now is going upward to join them. T has 1. And so when it goes upward, it becomes minus 1. Minus 2 minus 1, mathematically, it becomes minus 3. So this is now the dimension for power. ml squared t minus 3. Now what is now the SI unit for power? Power is measured in watts. Watts. Energy is in joules. Work done is in joules. Power is in watts. Power is measured in watts. One could also say that from here, kilogram meter per second square as the SI unit all over second square. So it becomes here, from here, let's put it down. Here as work done is almost saying that from here now, I have mass as my kg for power now. Power is work done is first time. This I want to call out the SI unit. If I'm not using watts, what else can I use? Work done is MA, which is first time distance. M is kg. A is meter per second square times over s over seconds. So this one becomes kg meter per second square. Another s going up, it becomes 3 meter cube. So this one also can be used as the SI unit for power. Power could also be kilogram meter per second cube or watts. Remember, I said we are evolving. So please, the standard unit for power is in watts. Energy is in joules. Sorry, energy is in joules, and equally work done is also in joules. Power is in watts. But if you are using this as power, you are still not wrong. It's the same. But just know that the standard unit for power is in watts. Talking about station power station, don't be talking about kilogram meter per second. No, we have about say 4,000 kilowatts. We have about I'm supplying light of say 2,000 watts, and have a transformer of supplying a whole station or supplying a whole city or supplying a whole street. You could say kilowatts. You're hearing the word kilowatt. You're hearing the word watt. You won't be hearing kilogram per meter per second cube. But that doesn't mean they're not saying the same thing. The standard unit for power is in watts. So let's continue. So we have talked about the dimensions of force, density, pressure. So we talked about pressure. Let's talk about pressure. Now, pressure. We talked about density, acceleration. We talked about force. We talked about work. We talked about energy, power. And let's talk about pressure. Pressure is force over area. Force over area. Now this is the formula for pressure. Force over area. Remember, force is MA. Force is MA, which is mass times acceleration. And then area is length times length. So it becomes L times L. So this is LT minus 2. LT minus 2 is the dimension for acceleration. Then M is the dimension for mass. Now, area is L square. L square is the dimension for area. Now, the SI unit for force is Newton. The SI unit for area is meter squared. Now, this now becomes the SI unit for pressure. This is how you combine it together. Now, why I'm putting N slash force is Newton slash meter square. Area is in meter square. So the SI unit becomes Newton per meter square. When you hear the word per, it means the division. Newton per meter square or Newton per meter square, depending how you want to pronounce it. Newton per meter square or Newton per meter square. We are saying the same thing. Now this is not the SI unit for pressure, but that is not the dimension for pressure. Dimension becomes MLT minus 2 over L2. Remember I said when you have a slash down, since I have L, I have to take it upward. So it becomes ML T minus 2. Now L minus 2 goes up because what? Minus 2 because it's positive sign going up. Now we already have plus 1 here. This is now the same as N times L1. I'm not supposed to put it there just because I'm explaining. L1 T minus 2 L minus 2 because 1 minus 2 becomes minus 1. So N L minus 1 T minus 2. This is now the dimension of pressure. I repeat again. Now, pressure is force over area. And force is mass times acceleration. Mass is N as the dimension. The dimension for acceleration is LT minus 2. We have done that. Then L square is the dimension for area because it's force over area. If I combine it together, it becomes MLT minus 2 all over L square. But I need to take it upward to balance it. Now, if this is plus 2, once it goes up, it becomes minus 2. So you have ML T minus 2, L minus 2. This L minus 2 is going up, it becomes minus 2. It's plus 2. Though I don't put the plus there, but you should know as a student, it's not there, but you should know that it's plus 2. So when it goes up, it becomes minus 2. And there's a 1 here. It shouldn't be here. I just put it here because I am trying to explain. It shouldn't be here. So 1 ML1 T minus 2 L minus 2. The L and L is the same. That comes to collection of like terms, mathematics. So L minus L1 T minus 2 L minus 2. So L and L come together. The 1 here plus 1 minus 2 becomes minus 1. So I'm having ML minus 1 T minus 2. This is now the dimension for pressure. Now, and the SI unit is in Newton per meter square. Newton per meter square. Okay? Now let's talk about momentum. Momentum. Mass times velocity. Mass times velocity is the, okay? Momentum, I said, is mass times velocity. That's the formula. Mass times velocity. Somebody will say, the formulas are becoming too much. That is why you are a student. You learn as many formulas as possible. They are for your consumption. The more you learn it, the more you become part and parcel of you. So mass times volume, mass times velocity is the formula for momentum. And mass is in kilogram, velocity is in meter per second. That is the SI unit now. Mass is in kilogram, velocity is in meter per second. So from here now, I have coined out the unit for momentum. That is why I tell you that SI unit formulas is very important. So you must know a formula. You can be able to coin out the definition, you can be able to coin out the SI unit. So now, if for instance I'm in the example and I've forgotten what momentum is, and after solving, and I'm asked to find the momentum of a given body with a mass and a velocity given, and I've forgotten the SI unit for what momentum is, but I should know that mass, since I know my formula as mass times velocity, mass is in kilogram, velocity is in meter per seconds. So if I know that, it becomes easy for me. So after solving, I should know that my answer becomes, whatever I have, let's say 10, is now 10 kilogram per second, and I'm referring to what? To momentum. So momentum is kilogram meter per second is the SI unit for momentum. Now, the dimension, we are doing on dimension. The dimension for mass is what? M, yes, and velocity is LT minus 1. LT minus 1. So it becomes MLT minus 1. This is now the dimension for momentum. And the SI unit is kilogram meter per seconds. The formula is mass times velocity is the formula for momentum. The SI unit is this, kilogram meter per second, and the dimension is MLT minus 1 as the dimension for momentum. Let's say impulse. 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 Represented as I and has the formula as Ft. Ft. And from there I can coin my SI unit. Force is in Newton, is already there, and time is in seconds. Now, force in terms of dimension, force is MA times time. M is M in dimension, A is LT minus 2 times T. Remember, once there's a symbol without any number on top of it, as from 2, 3, 4, is represented as it is now. M here is 1, but L also here is 1, but T is minus 2. That's once it gets to 2, 3, once the number is from 2, 3, 4, you can put it there. But once it's 1, you don't put it there. You just know that it's 1. So M here is 1, L here is 1, T is minus 2, then T here is also equal as 1. So if it's 1 here, it becomes, this now becomes M, L, T minus 2 plus 1, because it's 1 and it's a positive sign. I'm not carrying it up, it's already up. If it was down, when I take it up, it becomes a minus sign. Now it is up there, so I'm not doing reciprocation, so it's still there. So this now becomes M, L, T minus 1. Minus 2 plus 1 is minus 1. This now becomes the dimension for impulse. M, L, T minus 1. Minus 2 plus 1. Mathematically, minus 2 plus 1 is minus 1. So M, L, T minus 1 is the dimension for impulse. Let's continue. I believe you are finding this interesting. If you have a question, you can put it down. If you have a question, you can send it in the comment section. I will get to answer your question very well. Now let's go to electric charge. Electric charge. Electric charge. Electric charge has a formula as current times time. Current times time. Current times time. Current is multiplying time. Current is multiplying time. Now, electric charge is equal, current is A. Remember, I said current is measured in ampere. And when we started this topic, I gave you some of the dimensions that are permanent, like mass, I said is M, I said length is L, I said T is T, capital T, and I said electric current is A, and I remember I said temperature is K, and then luminous intensity as double L, double light number. Now, this electric charge is current multiplying time, and current, the dimension for current is A, and T is what? T. So it becomes AT. AT is the dimension for electric charge, and it is measured in coulombs. The coulomb, the SI unit for electric charge is coulomb. This charge is measured in coulombs. Now let's go for another one. Let's look at electric potential. Electric potential. Electric potential. Electric potential, which is voltage also. Electric potential is voltage also, and it's power over current. Power over current. This is V. Power over current. Power over current is the formula for electric potential, which is equally in voltage. And then remember we said power is force times distance all over current. From the formula now, force times distance over time all over current. Power over current is the formula for electric potential, and is power is force times distance over time all over current. Now let's break it down. You have force as MA times L is the dimension for distance all over T all over A. A is the dimension for current. And then this one, MA times L over T all over A. M should remain as M. A is now LT minus 2 times L all over T all over A. Now if this L, remember L here is 1, L here is 1. So L becomes 2. L becomes ML square. Now T here now is a positive sign. Going upward becomes a negative sign. So T becomes minus 1, which is minus 2 minus 1 is minus 3. T minus 3 all over A. Let me go back again. I said, okay, let me make space so that you will understand very well. Okay. We said voltage is power all over current, and power is force times distance. Force times distance all over time. That is power. Then over current, which is this. Now F force is LA times L. L is the dimension for distance. Over time, T is the dimension for time. Over the current. And then we said MA is ML T minus 2. The M is still there. M is mass is still M in dimension. As acceleration is LT minus 2 times L, which is the distance, all over T, then over the current. Now, ML, remember we have one L here. That means there's one L here, there's another one L here. So L times L becomes L squared. So you have L squared, then T. T is minus 2 here. This is 1 here. If I take it off, now it becomes to minus 1. So the T becomes minus 2 minus 1 minus 3. So it becomes ML squared T minus 3 all over A. If I'm carrying this A upward, remember, A now is representing 1. So if you go upward, it becomes what? Minus A. So the dimension becomes ML squared T minus 3 A minus 1. This is now the dimension for electric potential. This is now the dimension for electric potential. ML squared T minus 3 A minus 1. The A is representing current. Dimension for current is A. So this is now the dimension for electric current. Okay, let's do one more. Capacitance. And also the SI unit for electric potential is volts. The SI unit is volts. It's measured in volts. Measured in volts. Now capacitor. Capacitance is charge over potential. Capacitance is charge over potential. Charge over potential. This is the dimension for, this is the formula for capacitance. I remember we said charge is current. We talk about electric charge. When we say charge is AC. We did before we say charge is AC. And let's break it down. What's the charge? What is charge? What is charge? We charge as current times time. Current times time. And then potential, what we just did just now. Potential is power over current. If I combine these two together, charge is current times time. Current multiplying time. That's why I'm putting it as AT. So A is current. It's CURENT. Current times time. So current is A, T is time. I've got it for charge. Now for potential is now power over current. Remember we said power is force times distance all over time over current. So this becomes, leaving the charge aside, F is MA times D, which is L, all over T, all over A. What we just finished just now. So we are having this, M represents M, is still there. A is LT minus 2, don't forget. LT minus 2 is the dimension of acceleration times L, all over T, all over A. And this becomes what? This one now becomes ML squared T minus 2. If T goes up, becomes what? Minus 1 all over A. So it becomes ML squared T minus 3 all over A. So if this A goes up now, it becomes ML squared T minus 3A minus 1. This is now the dimension for potential. So put it together. For capacitance now, capacitance. Now we said capacitance is charge over potential. You know what charge is? The charge is 80 from our dimension. Charge is 80, and then capacitance, I said, is charge over potential. Potential now is what we have just done, and we have ml squared t minus 3a minus 1. If I combine it together, capacitance, which is 80, which is charge, over potential, which is this. If I now put it together, now remember I said whatever that is up has to go down, has to move up, and if it's a positive sign, to change to a negative sign. Now 80 is still up, nothing is affecting it. Now n is going up. Remember n is 1. So when it's going up, it becomes minus 1 because it was positive 1. So it's going upward, it becomes minus 1. L squared now is going up, it becomes L minus 2. Somebody will ask you a question, how come I'm not putting 1, as I was saying before, when the number is 2, 3, 4. When it's a negative sign, it is 1 and it's plus 1, you don't include it in your calculation. You just know it. But when it's a negative sign and it's 1, it's supposed to be there. That's why we are saying n minus 1 is going upward. If it was a positive sign, if it was a negative sign, it's going upward. I'm leaving it like that. I won't touch it. Now, let's continue. L minus 2 is L2, which is positive sign, is going upward because minus 2. T3 is going upward because what? T3. Remember minus is not plus. Then A, which is minus 1, is going upward as A. So I will put the plus 1 again. So A is minus 1, it is going upward, it becomes A, which is 1, positive 1. So let's put it together. We have A here, we have A here. So A times A is A squared. Then T, we have T here, we have T here. And we're now collecting of the like terms. Now T is 1, T also is 3. 1 plus 3 is 4. So T4, N minus 1, L minus 2. Now this is now the dimension for capacitance. 8 squared, T4, N minus 1, L minus 2. This is now the dimension for capacitance. I think we have gone through what dimension is. Let's go through what we just did today. We talked about the dimension of physical quantities. Dimension of physical quantity. When we talk about what dimension is, we say it simply means the way we can relate and connect physical quantities to fundamental quantities. Physical quantities to fundamental quantities. And we also said this method of dimension can be used to find a relationship between other quantities when mathematics becomes difficult. It's used to solve find a relationship between other quantities when mathematics becomes difficult. And we started with the major 3 most important basic quantities. Talk about length, mass, and their dimension. Remember I said that dimension is quite different from SI units. And I said length has a dimension as L, but the SI unit is what? Meters. Distance is measured in kilogram, but the dimension is L. And then we said temperature. Temperature is in Kelvin. That's the SI unit, is in Kelvin. And the dimension is K. And we also said luminous intensity as L, double L, not L per letter, not L, but just like double I. That is the dimension for luminous intensity. Then electric current, and we said A is a dimension for electric current, and it is measured in ampere. And we did a lot of calculation how we can find a dimension for acceleration, for velocity, for speed, and we talked about the difference between speed and velocity. We went over to talk about the dimension for capacitance, for pressure, and so a lot of them, we went through them. So please go through this video again and pay attention. Go, if you have any question, you make a comment on the comment section and I will answer you very correctly. So thank you and goodbye.